Welcome back, everybody. So we are in section 5.8. We've got 2 sections to go, and they're both going to involve one last new function that we will look at, which is the inverse trig functions. So we looked at exponentials and logarithms, which are inverses of each other. We've already looked at trig functions. Now we're going to look at inverse trig functions. So we'll just kind of remind ourselves here of what those trig functions are. So when we define sine, cosine, and tangent, those functions in and of themselves, so sine for example, are periodic. So they keep repeating. And because they keep repeating, they fail the horizontal line test, which means that the inverse of those functions, if we were to graph the inverse of the functions are going to not be functions themselves, right? They're going to fail the vertical line test. So if this is the graph of y, and this is the graph of y inverse, they don't work. So we restrict the domain of sine, cosine, and tangent in order to make them functions, so that then we can operate like normally. So we can differentiate, integrate, find rates, and also, use them in smaller application on specific domains. So for sine x, we restrict between negative pi over 2 and pi over 2. For cosine, we restrict between 0 and pi. And then tangent, of course, we just restrict between the two closest vertical asymptotes to the origin. So if we look at the sine graph, we can see that the sine graph is increasing everywhere here. And it is going to take on every value from -1 to 1 exactly once. Same is true for cosine. It's going to take on -1 to 1 exactly once. It is, however, going to be a decreasing function. And there are also going to be inflection points. So if we look at my sine graph here, we should be adding in a little bit more curvature there. So there's going to be an inflection point at 0, it looks like. And so we're going to be able to describe the behavior of these functions, find areas underneath them, and apply them accordingly. So these are all of the original functions, which means we now need to interpret the inverse functions. So if we're interpreting the inverse functions, of course, we swap the domain and range. So for example, if we're looking at sine inverse of y, our x-axis then becomes between 1 and -1, and our y-axis now become the angle measures. So we know that -1 is going to pass through negative pi over 2, and 1 is going to pass through pi over 2. And then what we're going to end up with is this kind of reversed function from the original. So note, it's going to be a reflection of the sine function about the line y equals x. Those are our inverse functions. It's just reflections. So we're going to get a shape sort of like this, which also has an inflection point, but has different concavities. For the cosine graph, it's going to be the same. So now it's going to be, again, between -1 and 1. And then we're going to start at 0 and go to pi. Oops. And pass through pi over 2 in the meantime. So at -1, cosine inverse of -1 is pi. Cosine of 1 is 0. And then we're also going to get that inverted curvature. And then tangent is a slightly more interesting function. So tangent is now going to have horizontal asymptotes at pi over 2 and negative pi over 2. And then it is going to travel across. Oops, that should be at 0. But it's going to now have this kind of infinite domain as opposed to a finite domain. And then it'll have a finite range. Range will be fixed between two values. that will be finite in length. All right, so those are our inverse functions. So what we want to do is we want to figure out how to integrate these and differentiate these. So up at the top here, we've got just some kind of reminder examples to kind of think about. What I've just discussed is kind of what this picture here is describing. So we'll discuss that a little bit more. But then I've also included kind of the standard definitions that we'll use for all of them. And just note arcsine is going to be some notation that we'll use, as well as that -1 exponential kind of expression. So you're going to see both notations interchangeably occurring quite often. So going back to the top, we can see that we want to find a couple of different inverse expressions. So we'll start with arcsine of rad 2 over 2. So the root question really is like, what are we finding here? So arcsine, remember, is equal to the angle measure. So our answer is always going to be an angle measure. So pi over something or some multiple of pi. And so the question that you should always ask yourself is, what angle measure of sine gives you rad 2 over 2? And so if we are thinking of all possible values, right, we could picture our unit circle, and then we've got rad 2 over 2 is going to occur at those 45-degree angles in the first and second quadrants only. So that would be pi over 4 or 3 pi over 4, and then we can include any multiple of those as well. However, we're restricting these as functions. So that means that the only one that we care about for arcsine for our function expressions is the first one, the very first value that we end up with. So our answer to this would simply be pi over 4 or 45 degrees. All right, same question for number 2. What position on the unit circle gives us a cosine value of 2? And of course, this is a trick question because 2 is out here, and there is no location on the unit circle because the unit circle is stuck at 1 at most. So this would be undefined. So again, those restrictions are going to matter quite a bit. But if we were looking for, you know, a arc cosine that has an answer, we could do arc cosine of 1/2. And arc cosine of 1/2 then is when x is equal to 1/2. Just going to put it up here. All right, so that's our x, which means our y would be rad 3 over 2, and that is going to be at 60 degrees, which is pi over 3. So unit circle stuff is going to be very, very useful, especially in example 3, because in example 3, we've got an actual undefined value. We've got x. So for these, you always want to start inside and then work your way outside. So we'll start with sine inverse of x. So this is an angle measure. So note theta is an angle on our unit circle. So let's draw in a little slope triangle. So we've got theta is there, and then the ratio for sine is opposite over hypotenuse. So that means that our opposite side is x, and our hypotenuse, of course, is 1, which means then that the adjacent side, if we use the Pythagorean theorem, is going to give us the square root of x squared. 1 minus x squared. Okay. And you could solve that by just doing like x squared plus y squared equals 1, and then solve for y. So now what we're doing is we're taking tangent of our angle theta. So tangent is going to be the opposite side over the adjacent side. So we'll simply end up with x over rad 1 minus x squared. And this is actually going to be the tool that we use to prove our derivative rules. So this is a very important idea where you're composing a trig function with an inverse trig function or vice versa, and then interpreting. All right, so we'll just make a couple of notes from what we discussed earlier. So trig functions are periodic, which means they have repeating behavior. trig functions are periodic and not restricted, let's say. In order to define the inverse trig functions, we must restrict the domain. So again, for our sine function, we restrict on the closest interval containing -1 to 1, which is, again, between -π/2 and π/2. And we get rid of the rest, so we ignore the rest. And the other nice thing too here is kind of a notation thing that's going to be useful to us. So note, if y is equal to sine x, that implies that x is equal to arc sine of y. So what that means is if I take sine inverse of y and I take sine inverse of sine x, since these are inverse operations, they cancel each other, right? So we can use that inverse as an operation. All right, and I've got some pictures of the graphs here as well that are a bit cleaner, a bit nicer looking. The ones that are kind of weird are arcsecant and arccosecant, but normally they're not going to give you anything where you need to worry too much about the range or domain, but you might just keep in mind when those values need to be positive. All right, so I think we're ready now to actually derive all of our derivative expressions. So we'll start with the most straightforward one, which is sine inverse of x. And we're going to start by drawing a triangle that represents our angle measure. So note, our right triangle on our unit circle, our angle is given by y. So note, y is our angle measure. And then our sides are going to be x1 and then rad 1 minus x squared as we saw before. So this is the same triangle that we saw in the the third example at the top. So what I'm going to do then is I'm going to take sine of both sides. So I'm going to rewrite this simply as sine of y is equal to x. So that's using that inverse property. So sine of sine inverse cancel out. So I'm just left with x on the right-hand side, and then I have sine of y on the left side. But now I've got just an implicit equation that I can now differentiate with respect to x. So if we differentiate both sides with respect to x, we'll get cosine of y times y prime, or dy dx, and then that's going to equal 1. So I'm just using an implicit derivative here, and so then y prime is going to be equal to 1 over cosine of y, which is just secant of y. But I can get secant by taking the hypotenuse over the adjacent. So what we end up with then is the derivative is going to equal 1 over rad 1 minus x squared from our triangle relationship. All right, so that's the derivative of arcsine. So the derivative of arcsine is just 1 over rad 1 minus x squared. So we'll do the same thing for the second example. So now we've got cosine. So y again is our angle measure, and then cosine is going to be the adjacent and hypotenuse lengths, the ratio of those two, which means we're going to get the 1 minus x squared on the opposite side. We'll do the same thing. Take cosine of both sides in this case, and then we can differentiate implicitly with respect to x. So we'll get negative sine y times y prime is equal to 1. So dividing by negative sine y, we'll get negative 1 over sine y, which is just negative cosecant y. So if I look at my ratios, then cosecant is going to be hypotenuse over opposite, which is actually the same exact ratio that we got with sine. So the only difference is it's going to be negative 1 over that expression. So one little quick note here just like with our derivatives of sine and cosine, they are just literally the opposites of each other. In this case, it's the opposite of the same expression as opposed to the opposite of the functions themselves. All right, let's go ahead and do tangent. So for tangent, we've got our triangle here. Y is our angle, and then it's going to be opposite over adjacent, which means now our hypotenuse is going to be a little different. It's going to be the square root of the sum of those squares, so it's going to be the square root of 1 plus x squared. All right, so we'll do the same thing we did before. We'll take tangent of both sides using the inverse property on the right side, and then again differentiating with respect to x. So we're going to get secant squared y times y prime is equal to 1, since the derivative of tangent is secant squared. So y prime is equal to 1 over secant squared, which is just cosine squared. So if we look at our triangle then, cosine squared is simply going to be 1 over the square root squared, so we just drop the square root. So we get 1 over 1 plus x squared. Okay. And so I will leave the work to you, but when we do cotangent, since that's got a relationship with tangent, the derivative of cotangent is simply going to be the opposite of the derivative of arctangent. So note, you can prove that those are the opposites of each other, which is really nice. Again, just by drawing triangles. And then we'll get the same relationship with cosecant and secant. So secant we can work out pretty quickly. So we'll work out secant here. So we've got y. So secant is hypotenuse over adjacent, which means that on this side, now we're going to have rad x squared minus 1. You can check that with the Pythagorean theorem. So we'll just take the secant of both sides and then differentiate both sides with respect to x. So the derivative of secant is secant tangent, or secant times tangent, times y prime. Again, because we're differentiating implicitly, we'll divide. So y prime is equal to 1 over secant y times tangent y, which we can see secant y we already have above is just x. Whoops. So this is going to be 1 over x times, and then tangent of y is going to be opposite over adjacent, so that's just going to be the square root of x squared minus 1. And depending on if we know the domain of our function, sometimes we'll put an absolute value on the outside of the x just to make it positive, which you'll see in the kind of general rules on the other side. But in general, we'll probably be given positive x values for most examples, so they won't really try and trick you with domains on these. So then it can be shown by the exact same method that the derivative of cosecant inverse is just going to be the opposite of the derivative of secant. So again, just opposites of each other, which means that we only really need to know 3. So the only ones we need to know are sine, secant, and tangent inverse. So if we know those 3, we know the other ones are just the opposite signs of those. So it's not like you need to remember 6, and the proof method for these is a really nice way to kind of start yourself working on these, because these can be hard to kind of start with without kind of deriving it a little bit. So just derive it if you feel you need to. So you don't have to memorize. You can always derive by using that inverse property and drawing that triangle that represents your inverse angle relationship. All right, so on the next page, we've got a cleaned up version of that. This is going to be the chain rule version. So instead of having the 1, we'll have a u prime times 1 over each one of those expressions. And again, we typically put the absolute value in case there's any domain issues, but there shouldn't be too many. So we've got a number of examples here, so I think I'll pause us here, and then we'll come back in the second part of the video to work out these remaining examples. So if you have questions, shoot me an email. Otherwise, come by the office hours. And until I see you next time, take care.